Lab 5, thanks for the memories. In this lab, I bump a volleyball and model the actual motion with models designed to approximate Newton's second law and the energy principle. Newton's second law, or the momentum principle, says that the change in momentum is equal to the net forces on a system, which is the total pushes and pull on the system, multiplied by the change in time. To use Newton's law to predict the future, we note that momentum is equal to the mass times the velocity. Therefore, with some algebraic manipulation, we can determine that the change in velocity over time is equal to the net forces on the system over the mass. In Tracker, I loaded the video of me bumping a volleyball. I set the calibration stick at 1.829 meters, which is my height, and the coordinate axis with the approximate center of the ball as the origin, with the positive x direction going right and the positive y direction going up. Playing the video, you notice the ball goes up and comes back down, and I noted the center of mass the entire way until it hit the ground. However, if you look at the graphs, something is obviously wrong, particularly in the x direction, and in our model we will see the errors that this leads to. Looking at the code in VPython, we set the variable ball.m at 0.26 kilograms, which is the weight of the volleyball, and the initial position at the vector 0.014, 0.004, and 0 in the x, y, and z directions, and all of those are in meters. We also have to set the initial velocities. To calculate the initial velocity of the volleyball, due to the way I hit the ball and how I set the tracker video and hit the different center of masses, I calculated at the times t equals 0.067 seconds and t equals 0.10 seconds, as my timing on the tracker was a little delayed. Looking at these formulas, I find that the initial velocity in x direction is 5.455 meters per second, and the initial velocity in the y direction is 7.576 meters per second, and I plug these values into VPython. Returning to the code, the net forces is equal to the gravitational force plus the drag force. The gravitational force is the mass times the gravitational constant in the y direction, and the drag force is equal to the proportionality constant times the velocity of the ball. After running several tests of the data, I see that I set the proportionality constant to be 0.005, which gives me the correct displacement in the y direction. Now if I run the program, you'll see that the ball goes in a parabola with the black arrow being the gravitational force and the little yellow arrow being the drag force. If you notice, the ball goes below the x-axis as the ball falls lower than the position that I set the origin at, which was where I hit the ball. Since it hit the ground and the ground is lower than that, the ball goes below the x-axis. Next, I imported the data into Google Drive and created a chart that compared the observed data and the modeled data. The blue lines are the x-coordinates. The light blue line is the modeled data, and the actual data, which I observed, is the dotted blue line. If you notice, the dotted blue line is very different than the modeled blue line. However, the red lines model the y-coordinates, which is the up and down coordinates. The model and the actual data appear very similar. There's a little hiccup at one point in the data near the end of the parabola, but overall it is very similar. Obviously, there are some problems with my model versus my observed data, especially in the x direction. I have two assumptions of why these problems exist. One is the initial velocity in the x direction that I determined was too fast in the positive x direction. Looking at the points, the ball actually went backwards from where I hit it and then forwards before falling near my feet. This was not captured in the modeled data. This is probably because I didn't hit the ball square and my tracker points might have been a little off when the ball was first hit. In other words, this probably would have went out of bounds or hit the net. Next, looking at the energy principle, two energies are definitely existing if we look at the model. One is the gravitational potential energy, and the other is the kinetic energy. Remember that according to the conservation of energy, the change in energy is equal to the change of energy in the system plus the change of energy in the surroundings. Here, I assume that the change of energy is equal to the change of potential gravitational energy plus the change in kinetic energy. I have added these equations into my Python code so I can graph the plot of the change in kinetic energy, the change in potential gravitational potential energy and the change in energy. If we run the module, we can see this graph. If you notice, the blue line is the change in kinetic energy, the red line is the change in gravitational energy, and the green line is the change in energy. Green line, which is the change in energy, should equal 0 if energy is conserved. Somehow there is other energy being involved in this situation. And last, I just want to say thank you for watching this video and watching all my other videos that I've had so far. This was a lot of fun to do, and it was a lot of fun to take all this class with all of you. Thanks. Bye.